Welcome to Maths with EJD. This is the second video on vectors. And here we are looking at vector operations. And straight to the point, the first vector operation we'll be looking at, or the first set of vector operations we'll be looking at will be vector addition and subtraction. They go together because it's just, it doesn't require any special thing. It's just straight to the point. So vector addition and subtraction, right? Talking about vector addition, vector addition. So the process of adding, two vectors, adding two vectors involves adding their corresponding components, their corresponding components. Okay, in the previous video, we came across this whole idea that we can have vector A to be, say, we can have AX, or better still, I can still use this. So it can be AX in the direction of I. Okay, that's overkill. AI plus BYJ plus, sorry, AXI plus AYJ plus AZK. And then you have B to be BXI plus BYJ plus BZK. So that if you're talking about addition, it means that A plus B will simply be adding the corresponding components of I, J, and K. So this will be AX plus BX, I, then AY plus BY, J plus AZ plus BZ K in the direction of K. That's basically what the addition of vectors is about. So then we go for the next one. Having talked about vector addition, let's talk about vector subtraction. Okay. Okay, I would have done this normally using this. But let me box it in that now. Okay, that's vector addition. So for vector subtraction, it's just about the same. It's just component-wise dealings. This can be visualized. This can be visualized as adding the negative of the vector to be subtracted, So it means that if we have vector A, which is AXI plus AYJ plus AZK, and we have vector B to be BXI plus BYJ plus BZK. All right. So A minus B will simply be component by component subtraction. So it's like A plus minus B, okay, which is simply AX minus BX in the direction of the unit vector I. You'll understand the idea of unit vector along the line, so don't worry. So AY minus BY in the direction of the unit vector J plus AZ minus BZ in the direction of unit vector K, as we have it. So that's the idea of subtraction. Okay, so let's take examples of this. Let's take examples. Okay, examples now. So now vectors can be represented in different ways. So for instance, I can say A is equal to 3, 2, 5. It is still the same as 3, 2, 5, any different ways, which is still the same as 3i plus 2j plus 5k. Okay, so it's just the same. So you can use any of the formats. So this is vector A, for instance, and vector B is, say, 1, 4 minus 2, 1, 4 minus 2. You can also say 1, 4 minus 2, and that is I plus 4j plus, plus minus 2k now. So that's actually minus 2k, like that. So we can talk about the sum. So if C is the sum, so we say C is equal to A plus B. So A plus B. And that's simply if we adopt the column vector. So that's 3, 2, 5 plus 1, 4 minus 2. 1, 4 minus 2. And that simply means you add component by component. So that would be 3 plus 1 there. Then 2 plus 4. And 5 plus minus 2, plus and minus is minus. So that's 5 minus 2. And then it means that your C, which you're looking for, C is actually 3 plus 2, 4, 2 plus 4, 6, 5 minus 2, 3. So that is your C, of course. So that means if you add A and B together, of course, this is the same thing as, if you like, you can call it 4, 6, 3. You can also call it 4i plus 6j plus 3k. So all the forms. So, but of course, you don't have to combine everything. I'm just using this to explain. So you can adopt whatever suits you. Okay. So let's assume that we now need to find the difference of these vectors now. So, and we want to call that difference D. So using the same vectors A and B, so we can have so this is vector addition now. So vector addition, that's what we are doing here. Vector addition. So for vector subtraction, so we take it that we have the same A, which is 3, 2, 5, 3, 2, 5, and we have B, which is 1, 4 minus 2. So let's see. D now, okay, this is A, this is B. So D now is A minus B. So that means we have 3, 2, 5 minus 1, 4 minus 2. So that means our D, which is the difference, is actually 3 minus 1, 2 minus 4, and 5 minus 2. Okay. So that's actually D, which is 3 minus 1 is 2, 2 minus 4 is minus 2, 5 minus minus 2, that's 5 plus 2, which is 7. So we have 2 minus 2, 7. So you can also express it as 2i minus 2j plus 7k, so all those forms. So with that, we've come to the end of vector addition and subtraction. So let's move on to talk about, scalar multiplication. Scalar multiplication. So we have done addition and subtraction. Now we are talking about multiplication, but there are different types of multiplication. That's why we are distinguishing between scalar multiplication, and we are going to see other forms of multiplication later. So scalar multiplication involves multiplying a vector by a scalar. A scalar is actually like a real number. Okay. So which scales the vector's magnitude? It scales the vector's magnitude without changing its direction. So the vector remains in the same direction, but its magnitude increases. Scales the vector's magnitude without changing its direction, unless the scalar is negative. Unless the scalar is negative. Of course, a negative scalar will change the direction of the vector. Unless the scalar is negative, in which case the vector's direction is reversed. In which case the vector's direction is reversed. Okay, so we have that. So let's take examples. It's really straightforward. Say we have if we have, for example, let A be equal to 2 minus 3, 4, and the scalar K is equal to 3. So the scaled vector B, which is equal to Ka, would actually be B. Let's not forget that we are dealing with vectors, so the arrows are important. Hope I've not forgotten at any point. Yeah, I think I'm good. So B is Ka, right? So K does not have arrow because it is scalar. So that's 3 multiplied by the vector A, 2 minus 3, 4. And that simply means that our B is equal to 3 times 2, 3 times minus 3, and 3 times 4, right? And B itself is actually the same thing as 3 times 2, 6, 3 times 3 minus 3 times minus 3 minus 9, 3 times 4, 12. So you can see the vector has been scaled. So it remains in the same direction, but the magnitude has been tripled. Okay. So that is that. Okay, well, I may want to also give another example for a negative scalar. So let's say that another vector, let's say C, vector C now is 4, 3, minus 7, and a scalar small c is actually minus 3. Okay, we've used 3 before. Let me just say minus 2. Okay. The scaled vector, D can actually, which is CC now, is given as D, which is equal to small c big C, and that is equal to minus 2 times 4, 3 minus 7. And we can straight away have minus 2 times 7, that's minus 8. And minus 2 times 3 is minus 6. Minus 2 times minus 7. Minus 2 minus 6 plus 7, 2 times 7 is 14. So in this case, the magnitude has been doubled, but the direction is changed. The direction of the vector is changed. Okay. So that goes. So that talks about vector scalar multiplication. And then we move on to the idea of dot products. So that's still some kind of multiplication. So we have dot product. Okay. The dot product, also called the scalar product. You know, scalar multiplication is different from scalar product. So also called the scalar product of two vectors. Now it is the dot product of two vectors is a scalar value. It's actually a scalar value. So if you need to multiply two vectors to get a scalar value, you have to do the dot product. So it is actually a scalar value obtained by multiplying corresponding components of the vectors and summing the results okay, to demonstrate that on a general term, we can say that for vectors A, which is A1, A2, A3, and vector B, which is B1, B2, B3. So the dot product A dot B is given like this: A dot B, and that is equal to, normally, right? So we have okay, to even I think this gives a better picture of what we have. So it's more like you have A1I plus A2J plus A3K, all this now, dot B1I plus B2J plus B3K. So, I once told you that I, J, and K are unit vectors. And we need to understand that as unit vectors, these following things hold about them. That so yeah, you need to note that I dot I is equal to 1 because they are unit products. So I dot I, okay, I think it's better to say I dot I, J dot J is equal to K dot K, and that's always equal to 1. Whereas I dot J is equal to I dot K is equal to J dot K. I mean, and if you reverse all the directions, Ji, Ki, and all that, so all the rest, everything will be 0. Okay. So in that case, since only I, J, J, and KK will work, it simply means that for this now, our A dot B will simply be so it will simply be A1, B1, because I and I will be 1, so that will work. But I and J will be 0, so it will cancel everything. Then I and K also 0. Then you go to A2, A2J, B1I won't work, that's 0. So you have just A2 and B2 because they are both JJ. So it's only JJ that will give you that. And then A2J and B3K won't work because J and K is 0. Like you have seen, the dot of them is 0. And lastly, you have A3K and B1I 0, A3K, B2J 0. But A3, B3 would work, A3, B3, because K dot K will be 1. So this is actually what we have as the dot product of those two vectors whenever you have two vectors like that. So, and that actually has a geometric representation. So, geometric interpretation of the dot product. So, the dot product can also be calculated using the formula A dot B is equal to absolute value of A multiplied by the absolute value of B times the cosine of the angle between them. Okay, cosine of theta, where theta is the angle, between the two vectors. Okay, And we already know how to calculate the magnitude of two vectors, actually. So, for instance, now we can even use this to calculate the angle between the two vectors. But let's take the example we have right here. So, we have this example. So, if you have A to be 2 minus 3, 5. You have B to be 4, 0, and 1. So that means A dot B. Never forget the arrows. As far as you can't show that it's the bold thing you're looking for. So this is like 2 minus 3, 5 dot 4, 0, 1. So what this is going to end up giving us is this. It's going to be 2 times 4 plus minus 3 times 0 plus 5 times 1. And that means this will be 8 minus 0 plus 5. 2 times 4 is 8, minus 3 times 0 is 0, 5 times 1 is 5. So it means that the dot product of A and B is simply 13, like that. The dot product is 13. Oh, is it 13? Or what did I do wrong? Okay. Yeah, if it is 401, yeah, we are fine. It's 13. Okay. It's 13. All right. So now you may be required, right, to find the angle between the two vectors. So if you need to find the, okay, I guess I want to change the marker here. So to find the angle, between the two vectors, say A, these same vectors we worked with, A, which is 2 minus 3, 5, and B, which is 4, 0, and 1 that we just worked with. To find the angle between them, don't forget the formula that A, we know already that A dot B is the same thing as the absolute value of A, that's the magnitude, and the magnitude of B, cosine of theta. So we are looking for this theta now. So if you need to get that theta, you can divide through by the magnitude of A and multiply by the magnitude of B. So you know that cos theta is actually, divide both sides by this magnitude. So you have A dot B all over magnitude of A, then magnitude of B, so that theta itself is arc cosine of A dot B all over absolute value of A, absolute value of B. So what does that tell us? We already know A dot B to be 13 from what we did before. So we know A dot B already is 13. So we have this. Then the next thing we need, absolute value of A, the magnitude of A. And, you know, the magnitude of A, like we know already, 2 minus 3, 5. That will simply be square root of square root of 2. I mean, square root of 2 squared, right? 2 squared plus minus 3 squared plus 5 squared. So that is magnitude of this equals square root of 2 squared is 4, 3 squared is 9, 5 squared is 25. So this is A, and that is 4 plus 9 is 13. 13 plus 25 is 38. So that's square root of 38, like that. Then, of course, we can find the magnitude of B. The magnitude of B, which is 401, that is square root of 4 squared plus 0 squared plus 1 squared. Okay, so the magnitude of B is equal to square root of 16 plus 0 plus 1. So B now, magnitude of B is root 17. Okay, and from the formula we have, you see that? So we can have theta. So therefore, theta is equal to arc cosine of course, let me just write the formula for the sake of it. This, and that is equal to arc cosine, or let me take it down. So let me take it down. Theta is arc cosine of A dot B is 13 all over root 38. That is magnitude of A multiplied by root B magnitude of B rather, which is root 17. So you need a calculator to get this done. So let me see. We can quickly refer to Desmos for this. So let me go Desmos. So Desmos now. So we have arc cosine of what now? 13 divided by square roots. Does this work? Yeah, great. Square root of 38 multiplied by no multiplied by, okay, still down there, square roots of 17. So that's what that gives us. Arc cosine, but this is not in degrees. Now let me see if we can get it in degrees. Can we say degrees? What can we do here? What can we do? This is actually in radians. This is in radians. Let me see what we can do. Can I say degrees? Degrees, does that work? Degrees. No, it doesn't. But what we have here is actually in radians. Let me see another thing. Okay, let me just take it to Google. Okay, let me just take it to Google. So this now in degrees. So if you have a calculator, we won't have to go through all this trouble. Okay. Can I just paste this here? Does this work? Okay. In this case, I don't think we need all these plenty things. So it's just simply 13 divided by square roots. Can we do square roots of 38? I'm not sure. Square root of 38 times square root of 17. I'm not sure if this is going to work. Let's just see. Okay, I mean, this doesn't work. Let me see. Okay, well, this is actually in radian, right? And we know how to convert in radians. So we can do that, although that's like a lengthy thing. Okay, let me leave this. Just punch your calculator and get the value of theta here. So that I don't keep moving around the place. Okay. So we got the answer there in radians, but I want it in degrees, which most people are used to, I think. So with that, we have come to the end of dot product. And then what we have left is the cross product. So let's do cross product. So far we've done addition of vectors, subtraction of vectors, scalar multiplication of vectors, dot product of vectors, cross product of vectors, and finally we have come to cross product. So when you do dot product, you get a scalar value, you get a number, like 13. But when you do cross product, you are going to get a vector. So when you multiply a vector by a vector and you get a scalar, that's dot product or scalar product. But when you multiply a vector by a vector and you get a vector, then that is actually cross product. So we need to understand that the cross product, which is also called the vector product, of two vectors in three-dimensional space. It can be in two-dimensional. Yeah, I think it can be in two-dimensional space too. Yeah, in three-dimensional space, in three-dimensional space, in three-dimensional space, it actually results in a new. So when you multiply these two vectors, it results in a new vector, that is perpendicular. It's a new vector that is perpendicular. That is, it makes 90 degrees to the plane containing the original vectors. So the plane containing the original vectors. So if we have vector A to be A1, A2, A3, and vector B is B1, B2, and B3, right? So the cross product A cross B now, the other one is A dot B. So this cross product is actually given by this setup. Of course, I'm forgetting my arrows here. I shouldn't ever forget because we're dealing with vectors. So A cross B is equal to, so now it's a matrix. Thankfully, I've treated matrices. So I, J, K. So I, J, K, I've told you before they are the unit vectors. So this is A1, A2, A3, then B1. So it is the determinant of this vector now. The unit vectors I, J, K, and A1, A2, A3, B1, B2, and B3. And if we expand the determinants, see what we get. So of course, this is how we go. So if you can start from here, and in this case, you cross out the row and you cross out the column, okay, and then you get I into, what do you have? A times 3, A2 times B3, then A3 times B2. So you have, so here you have I into A2 B3 minus A3 B2. Okay, so that's when you take the I out. So on the other hand, carefully remove this. So then you go for the next unit vector right there. And now, so this is the focus. And because this is the focus, cross out the row it belongs to and the column it belongs to, such that, so, of course, you also have to assign signs to it. This is plus, minus, plus normally. And the reason is because you say minus 1 raised to power, it belongs to row 1, column 1. That is 1 plus 1. And that is minus 1 raised to power 2. And minus 1 raised to power 2 is minus 1 times minus 1. And the answer is positive. So plus 1. So that's why this one has a plus. Then for the second one, this J cap actually belongs to row 1, column 2. So it means you have minus 1 raised to power 1 plus 2. And that is minus 1 raised to power minus 1 raised to power 3, which is minus 1 times minus 1 times minus 1, which is still minus 1. So you have minus here. And then this one is row 1, column 3. That is minus 1, row 1, column 3. That is minus 1 raised to power 4. And that is plus 1. That is why you have plus, minus, plus, in case you're wondering how that comes about. That's what I've just explained. Okay, so we can have actually this. So for J now, so pay attention that the sign has changed. So you have minus J cap into, so since you have crossed this out, so you have A1 times B3, A3 times B1. So you have A1 B3 minus A3 B1. Okay, so that's the other part, and we are not done yet. So you have to use the three elements on that first row of the matrix. So let's carefully remove all this. Okay, now our attention shifts to K. So for K now, it belongs to row 1, cross it out. It belongs to column 3, cross it out. So then we have A1, B2, A2, B1. Okay, so it means we have, but the plus is what we have up there. So you have plus K into A1, B2 minus A2, B1. And that is what we have for that. So that's simply cross products. So it's a bit trickier than dot product. Dot product is really straightforward. So this is what we get for A cross B. That's cross products. Okay. And of course, it has a geometric interpretation, just like the dot product has. So for the geometric interpretation, see what we get. Geometric interpretation. So we have the magnitude of the cross product, cross product vector is given by, check, the absolute value of A cross B. So when you do A cross B, whatever you get is actually equal to the magnitude of A multiplied by the magnitude of B. Then sine theta, the other time it was A dot B equals magnitude A magnitude B times cos of theta. So in this case, theta is the angle, where theta is the angle between A and B. Okay, so we have that. So let's take an example. So we say example. So imagine that you have a vector A, which is 1, 2, 3, 1, 2, 3, and you have B, which is 4, 5, 6, 4, 5, 6. Okay. So the cross product C, which is A cross B, is actually the same thing as C now equals determinant of I, J, K. So that's, you have 1, 2, 3, then this is 4, 5, and 6. And then if you expand the matrix, expand the determinant actually, so you have I, just like I said before, so if you are considering I, cross the row, cross the column. So that's okay. So because this is I, so first of all, you are considering I, cross the row and the column, cross the row, cross the column. So you have I into, then of course this is 2 times 6, 5 times 3. So you have 2 times 6. Okay, let me just do this. Okay, this is just for the sake of clarity. That is 2 times 6 minus 3 times 5. Okay, we have this. And then the next thing, our focus shifts to J now. So if you're focusing on J, delete the row, delete the column J belongs to. But of course, don't forget this is plus, minus, plus as usual. So then you have minus J into, so now 1 times 6, 3 times 4. So you have 1 times 6 minus 3 times 4. Then finally, you can focus shifts to K. Our focus shifts to K. So we have K in focus, delete the row, delete the column, and then you have 1 times 5, 2 times 4. So, but K has a plus on top of it. So you have plus K into 1 times 5 minus 2 times 4, like that. So you can now simplify all this. So you have C to be I into, so I into 2 times 6 is 12, minus 3 times 5, that's 15, then minus J. That is 1 times 6 is 6, 3 times 4 is 12 again, plus K now into 1 times 5 is 5, minus 2 times 4, that's 8. So with that, we have it all tidied. And then we have C now to be I into 12 minus 15 is minus 3, minus J. 6 minus 12 is minus 6, plus K. 5 minus 3 is 5 minus 8 rather, is minus 3. And then we go to the final step where we state the last answer. So C is minus 3I plus 6j, of course, because minus and minus is plus, then plus and minus is minus again, minus 3k. So which you can actually write as minus 3, 6 minus 3. So that is the cross product. Okay, well, to stretch it further, let's talk about that geometric interpretation we did the other time. So let's say I want to find the angle between A and B. So to find the angle, so I can say to find the angle, between A, which is 1, 2, 3, 1, 2, 3, and B, which is 4, 5, 6. We can still do this using dot products, but that's how I'll specify using vector products. Okay, so what we have to do here is to say that the A multiplied by B, the cross product, the magnitude of that cross product is equal to the magnitude of A multiplied by the magnitude of B sine theta. Now it's sine because you're using vector product, and then theta is what we are looking for. So it means we have to divide through by A cross B. So it means that sine theta alone is equal to the magnitude of A cross B divided by the magnitude of A multiplied by the magnitude of B. Okay, so already we have A, right? A is 1, 2, 3. So the magnitude of A we know is going to be the square root of 1 squared plus 2 squared plus 3 squared, and that is square root of 1 plus 2 raised by 2, sorry, 2 squared, 1 plus 4 plus 9. So 1 plus 4 is 5, 5 plus 9 is 14. So magnitude of A is root 14. Magnitude of B is 4, 5, 6. B is 4, 5, 6. That's 4 squared plus 5 squared plus 6 squared. And that is square root of 4 squared is 16, 5 squared is 25, 6 squared is 36. So 16 plus 25 is 41, I believe. Yeah, 41. Then 41 plus 36. 41 plus 36 is 77. Interesting. 41, right? Yeah, that's 77. So we have roots 7, 7. And then we also, in this case, we also need the magnitude of A cross B. And don't forget, A cross B is minus 3, 6, 3, 6 minus 3. Minus 3, 6 minus 3. So the magnitude of A cross B is square root of minus 3 squared plus 6 squared plus minus 3 squared. So that is square root of 9 plus 36. 9 plus 36. Minus 3 squared is 9. 6 squared is 36. Minus 3 squared again is 9. So that's square root of 9 plus 36 is 45. 45 plus 9 is 54. That's root 54. So the angle, did I even complete this? So this simply implies that theta is arcsine of the magnitude of A cross B all over the magnitude of A multiplied by the magnitude of B, like that. So that is your theta. So we can just simply say, therefore, theta, which is arcsine of A, arcsine of A cross B, all over magnitude of A, magnitude of B, is actually theta equals arcsine of the magnitude of A cross B is root 54 all over the magnitude of A is 14. Magnitude of A is 14. That's square root of 14. And then the magnitude of B is square root of 77. So if you punch your calculator for this, you can actually get the result. So we come to the end of vector operations. If you have not subscribed, be sure to do that and hit the notification bell so you can always get alerted each time a new video is released. And be sure to comment, like, and share. So watch out for the next set of videos on vectors. Until then, see you. Bye.